All right, we're back after a short break, and hopefully you figured out the answer to this one, or maybe even remembered it from 341 because we talked about it there too. But we have a pressure level meter at this spot, and it's going to experience sort of alternating pressure increases. We've been calling compressions, and then all the pressure decreases in the form of rarefactions. So kind of going down through the middle here, what does the output of that pressure level meter look like as we chart it over time? In the simplest case, it's going to be a sine wave pattern. So it's going to be alternating between high and low pressure values. And I kind of hear, so this is called a sine wave. It's a mathematical construct. You might recall it from math class in high school or wherever. Normally, sine waves are actually, technically, sine waves are supposed to start at 0 and then go up to 1 and then down to -1, so on and so forth, and alternate that way. I charted this as starting at 1 because in this previous slide, I have the start as a compression rather than rarefaction. Either way, they look like this, so it's kind of smoothly alternating up and down in terms of its pressure as it's charted over time. And they sound like this. So that's kind of the most basic sound you can have. And it's very not that interesting to listen to, right? Sometimes it's called a pure tone for that reason. But when we plot this out in what's called a waveform, it looks like this. It's just pressure as it changes over time, which is what all sound waves have to do. They have to show changes in air pressure for us to perceive them as sound somehow. So this is just a technical definition of waveform, plots air pressure on the y-axis against time on the x-axis. And this is a more true sine wave because it begins at 0, but it shows you that same kind of alternating up and down pattern, right? This also gives you a couple of nice little definitions in case you need, your memory needs jogging as far as they're concerned. So this is the peak of one cycle of the sine wave pattern, the highest point, the highest amplitude or the largest amount of pressure in the sound wave. And then there's one cycle here, which is when it starts at 0, right? And then when it picks back up again at the next 0 crossing and starts the same pattern all over again. This whole up and down and back up again pattern is one cycle of the sine wave. Okay, so that's the basics of acoustics that I want you to remember. This is analog acoustics, at least in the way we normally think about it in the real world around us. So here's where I make a distinction between analog and digital. Excuse me. So in reality, whatever that might be, sound is analog, or at least for all intents and purposes it is analog, which means that the variations in air pressure are continuous. In other words, it has an amplitude value at all points in time. There's no sort of gaps in between the different amplitude values. And there's also an infinite number of possible air pressure values. It can be as intense or as whatever the opposite of intense is, as it wants to be. The compressions can be as big, the rarefactions as small as they need to be. Now, I'll pause here because I'm going to post this on the internet. Who knows who's going to watch this? And it's also for your benefit too, but if you get to the really, really small microscopic subatomic level, there are limits on sort of the analog nature of reality, things like Planck's constant and so on and so forth. We don't have to worry about that. For this, I'm just going to talk about sound being analog. You can kind of think about this like an old-fashioned clock face, where you have two hands which are just kind of moving around in a circle, and there's no sort of clear jump, no quantum leap, as it were, from one time to the next. They just keep on moving, right? At least that's the way it appears to us. Back in the bad old days of my youth, and before that too, acoustic phonetics was strictly an analog endeavor. So if, say, you wanted to go make a spectrogram, you had to get one of these beasts, which is a spectrograph produced by the Sonograph Corporation. It was just kind of this huge, heavy piece of equipment that would sit in like the corner of a phonetics lab, and it would have this kind of rotating drum of carbon paper on the top, and somewhere in here you'd speak into a microphone, and this thing would turn around and it would, through whatever electro wizardry, would convert your voice or what you said into a spectrogram on the spot in physical form. So like I said, this is the case even as recently as the 90s. So I went to college in Southern California at a small school kind of in the, well, it was in Claremont, San Gabriel Valley. I had trouble remembering the valley it was in. So it was about 35 miles away, as far as I knew, from the nearest spectrograph, which was at UCLA. So we were not actually able to make spectrograms back in those days, even though it was a pretty decent program I was enrolled in. We would have to, if we wanted to, travel 35 miles down the freeway through LA to the west side and make a spectrograph or spectrogram using this machine at UCLA, which we never actually did because that was too difficult. So consider yourselves lucky that you live in the 21st century, because now we can just do this digitally using a computer. So to do this, though, we have to make a few simplifications, which is what I'm going to talk about in the rest of this lecture. So in a computer, everything has to be represented in discrete form. So everything has to be either a 1 or a 0, like an open or a closed circuit, basically, at some level in the computer's machinery. So you can think about this in contrast to the old analog clock face, like a digital clock, which is what most people use nowadays, although not everybody. But when this changes time, it makes like a quantum leap, right, from 1 minute to the next. So 257 to 258, so on and so forth. There's no sort of continuous motion. It's just boom to the next one, boom to the next one, and then there's stasis in the middle, right? So that's a digital clock. You can think of digitally represented sounds in a similar way. So we're going to see instead of continuous time and continuous air pressure values, we're going to see instead discrete pressure values at separate points in time. So we have to make a conversion from the analog reality that sound exists in to the digital representation, which makes everything nice and discrete, puts everything in nice little boxes for us that a computer can handle well. So we make a few sacrifices, which won't be that big of a deal as long as you know how to recognize them, and we get a huge amount of power at our fingertips, right? Because we can do this just on the fly using a computer and using prot, so on and so forth, rather than having to travel 35 miles down an LA freeway, which we don't really want to do, and making some spectrogram using a piece of equipment from the 1950s. We can have the best of technology at our fingertips, and what we get out of this, like I said, is discrete pressure values at separate points in time using a finite number of pressure values and a finite number of points of time. And one of the reasons why is because your computer is not an infinite machine. It can't store all the possible values of the world in it. It's got its own limitations. Thankfully, though, computers are powerful enough nowadays that these limitations don't have that much of an effect on what we can do. But there are some. Okay, so we're going to learn about analog to digital conversion. This is often called A to D conversion. The specific algorithm I'm going to talk about is also known as pulse code modulation. Pulse code modulation, or PCM. So what happens here is that when computers record sound, they need to digitize analog readings in 2 dimensions. So the 2 dimensions we see on a waveform, right? There's the time dimension, and then there's the amplitude dimension. When a computer converts something analog in the time dimension into something digital in the time dimension, it's called sampling. The same process in the Y dimension or the amplitude dimension is called quantization. I'm going to walk through those 2 dimensions in a fair amount of detail as we go, but keep them in mind. This is what they mean. Sampling is what happens in this dimension, putting everything in boxes in the X dimension, and then quantization bends everything up in the Y dimension. So we get ultimately a nice little grid of sampled, quantized air pressure values as they change over time. Okay, so here's an example of kind of the output. We've seen this before. What I did here was I said the word sampling, just like that, and I recorded it using prot. And I'm looking at just a very brief little snippet of it here. So I took it, I recorded it in prot and kind of exported it to an Excel file so I could play around with it a little bit more easily. And I'm just grabbing here, this is about 11 milliseconds of this particular waveform. And you can see air pressure changes, it bounces up and down over time. This is time in this dimension, and this is air pressure converted into electrical voltage in the computer. So this has already been digitally converted, but we can use this as kind of a metaphor because it looks at this level of a sampling rate, it looks like it's analog, like these changes are continuous. We can't see the individual kind of dots, which represent the values of the sound wave as it changes over time. So these specifically, I just did this morning for fun, because this is what I do for fun in a pandemic. So these are samples 13,500 to 14,000 of this sound file. And it's sampled at 44,100 hertz. So what does that mean? So when I sample things, all I need to do is just record the amplitude value of the sound wave at regular intervals of time. So I pick one sample here, and then the next one is this far down the road time-wise. The next one is same amount of time later, so on and so forth. In each one of these blue lines, I need to pick a value of the sound file and just record it. Record its amplitude value. So I know what time it is because they're all evenly spaced, and I'm just going to grab the amplitude value at that particular point in time. So I'm going to circle which amplitude value I get as we go down the line here. And hopefully you can see that fine on your computer screen. And I'll just mention as I go here that when I say sampling rate, the sampling rate for this original sound file was 44,100 hertz, which means that 44,100 times a second. Prot was sort of making a note of what the amplitude value was of this particular sound wave. And it came up with this orange line. We're going to walk through simpler or like smaller and smaller sampling rates as we go to kind of get an understanding of this process. But basically, again, at this point, you'd say, well, the amplitude value of this sound wave is this, whatever, it's a little more than 0.1. At this point, it's a little bit less than negative 0.1. At this point, it's 0.1 again. At this point, it's like 0.15, so on and so forth. It's a computer. It's mind-numbingly boring, but the computer can just repeat very quickly for basically as long as you want it to, so it can record these values very quickly and create a representation of the sound wave out of them. And this is the point where I pause, or at least somebody's probably going to ask, well, you're getting this value of this sound wave here, and you're getting this value of the sound wave here, but you miss this little jagged up and down stuff in the middle. The computer is not recording anything at all in between these blue lines. So you miss these two bumps, you miss this bump down here. The computer's just going to think you're going to go from one of these circles to the next. You're going to miss this stuff. This one's fairly close to the reality, but you don't know. You don't get that stuff in between the blue lines, so you never see it being a reality or not. Okay, so some people are troubled by that. They're like, well, why can't we just record all the values? And you could if you really wanted to, but it turns out that not all of the values matter. So I'll give you an example of what it looks like when you record at a lower sampling rate. So this is, again, 44,100 hertz, 44,100 times a second. I'm taking amplitude values. I'm going to cut that by a tenth. So this is a sampling rate of 4,410 hertz. So I just took every 10th sample to give you this representation. And you will see that it looks simpler than it did before. So I'm not getting quite as many little bumps and jagged edges in this sound wave as I had in this representation. This looks kind of nice and fluid and, well, also a little bumpy too. This one seems a bit simpler, and it's kind of more edgy, doesn't have kind of the nice continuous flow as the previous one. And that's because I'm only getting a tenth of the information as I got in the previous one. It looks fairly similar. It's just sort of like not as fleshed out, right? So this is not doing that bad of a job of representing the sound. Whoops. But it's the same exact sound, just sampled at a different rate. So yeah, you lose some information. So since I did this morning, I'm thinking about this just to make sure we're on the same page mathematically. So if you have samples 13,500 to 14,000 of a sound file, how many samples do you have, class? This might jog your mind a little bit again. Because I'm including kind of both ends of this, it looks like it's 500. It's actually 501. If it helps you to understand this, you can bump up both of these numbers by one, then you go 13,501 to 14,001. Yeah, so that gives you 501, not 500. You get both the edges. So if that sound file is sampled at 44,100 hertz, how long are those samples going to last? That's the question that I'm not going to answer for you now. I am going to let you figure it out on your own, and then I'm going to come back with part number 3 of this video. So come up with an answer, start watching part number 3. See you then.